In this video, we are going to look at transformers. Transformers work by mutual induction. This is when a changing magnetic field in a coil causes an EMF in a neighboring coil. So the diagram here shows a primary coil just next to a secondary coil. So when this switch is closed, current starts to flow in this one. Now, since there is a change from 0 to a maximum of current, there is going to be a current induced in the secondary coil. Now, since this is DC, the galvanometer deflection will go back to 0 because there's no more changing magnetic field in this one. However, if you constantly change the variable resistor here, increasing and decreasing it, you are going to have a continuous deflection on the galvanometer here. From that is back and forth like that, left to right and back again. That is when you have a rheostat being adjusted constantly. Also, if you switch on and off here on the switch, you're also going to get a deflection, or you're going to get a continuous inducing of current in the secondary coil. So there are two things here. That is, you could change or adjust the rheostat, or you could switch on and off multiple times on the switch. The moment you stop switching on and off, then nothing will take place here. So remember, from my video on electromagnetic induction, I said that there has to be a changing magnetic field to induce an EMF in a conductor, in this case in the secondary coil. Now, the two coils do not necessarily have to be in electrical they don't have to be in electrical contact. They have to be insulated from each other. As long as the magnetic field lines are linking this secondary coil, you're going to get an EMF induced here. Now, let's look at how this EMF is going to be, also taking into consideration Lenz's law. Now, when you close this switch here, you do have a current that is flowing from positive to negative, like that. Now, positive is going to go up there, down the other side, up here, up here, up here, and up here, then down back again to the negative. So which means all these are going to be arrows pointing upwards. So by the right hand grip rule, your fingers must curl it upwards. Then if you do that well, you find that your thumb will be pointing towards the left. Your thumb points towards the left. If you do that, please do it with your hands, the right hand, please. So using the right hand grip rule, you find that the thumb will be pointing that side, and the other fingers will be pointing upwards here. So remember, from the right hand grip rule, the thumb points in the direction of the North Pole. So that side will be North Pole, and then the South Pole will be this side. By Lenz's law, the coil here is going to induce a South Pole, so that work done to overcome repulsive forces here is equal to the electrical energy that is then created, or that is then formed over here in the secondary. Therefore, you do have a South Pole here. So when we have a South Pole here, which means our North Pole is going to be there, apply the same right hand grip rule. You find that the other fingers will be now pointing downwards here, and your thumb will be that side. That's the right side. So if you do that, you find that your current will be flowing in an anti-clockwise direction, like that. So anti-clockwise direction from positive to negative. So something like this. So you're going to get a current flowing this way. Now, when you open the switch, then there's going to be a decrease in the magnetic field lines being linked to by this coil. Therefore, current reverses direction and goes in the opposite here clockwise, and there since there's a decrease in the magnetic field lines. Now if you have constant changes in the adjustments in the rheostat, you're going to have similar behavior, that you're going to have sinusoidal waveforms that are going to be formed. Okay, so I think I have explained what is here. Now the size of the induced EMF is increased if there are more turns in the secondary coil. So if you increase the number of turns in the secondary, you also increase the EMF that's going to be induced in the secondary. If there is a soft iron rod linking the two coils, because the rod gets magnetized and concentrates magnetic field lines to itself, thereby increasing the magnetic field strength. So if you put a soft iron core here and insulate the wires so that there is no electrical contact between the wires and the soft iron core, you are going to have the magnetic field that's going to be created there is going to be strong enough. So which means you're going to have more EMF here induced. Let's see if I left out something else. Right, so the direction of the induced current in the secondary is given by Lenz's law. I've explained how it is done, so if I can just go over that, you then understand. Right, in practical transformers, before I look at practical transformers, this is an experiment that I often carry out when teaching this topic on transformers. So you've got two C core clipped together, and then you have a primary coil connected to a 1 volt AC supply. It is 10 turns. Then we've got a secondary coil which you vary the number of turns on the secondary coil, that is from 5 to 15 turns. Observe what happens when you vary the number of turns here. Okay, connect a lamp across the secondary coil. So let me use this as my example. You have two C cores joined together to form this, and then you do have a primary coil connected there, secondary coil connected there. Now we are varying the number of turns here in the secondary, and then observing what happens to the brightness of the bulb that is here. You connect a bulb here, that's the lamp, or you connect directly to a CRO. A CRO is a cathode ray oscilloscope, which basically tells you the waveforms. Okay, it displays the waveforms that is for PD, and that is for current as well. So we normally observe the brightness of the lamp when the number of turns on the secondary is varied from 5 to 15, and also when the C cores are pulled apart slightly, and see what happens there. The magnetic field becomes weaker, and then you have less EMF induced in there, and then less brightness. Now, how transformers work. The primary coil is connected to an AC supply. Why AC? If you watch my video on alternating current, you learn that alternating current is formed from electromagnetic induction, and this is current that is constantly changing after every half a cycle. So when you apply alternating current there, it means that you're going to have a changing magnetic field created in the. Remember, every conductor that carries a current has a magnetic field around it. So if the current is changing, you get a changing magnetic field also produced. Now this magnetizes the core, and then since this is a changing magnetic field, it's going to induce a current in the secondary. So that's how transformers work. So the type of current that is induced again is alternating current. So now the amount of the amount of EMF that's going to be induced there depends on the ratio of these turns here. If you've got more turns in the secondary coil than in the primary coil, we're going to call that a step up transformer. So you get more voltage there and less current. If you have more turns in the primary than in the secondary, you have what is called a step down transformer, and the voltage is stepped down while the current is stepped up. Now for an ideal transformer, the voltage across the secondary Vs divided by the voltage across the primary Vp is equal to the secondary turns divided by the primary turns. So the number of turns in the secondary divided by the number of turns in the primary, Ns. So Vs over Vp is equal to Ns over Np. A step-up transformer, like I said, it has more turns in the secondary than in the primary, so the output voltage is greater than the input voltage. Whereas a step-down transformer has less turns on the secondary coil than on the primary. The output voltage is less than the input voltage. An ideal transformer is one that is 100% efficient, which means that the power in the primary should equal the power in the secondary. Now the formula that we use to find power is voltage times current. So voltage in the primary times the current in the primary is equal to the voltage in the secondary times the current in the secondary. So VPIP is equal to VSIS. Now if you group like terms together, you have VS over VP will be equal to IP over IS. That is it. Now we're going to look at that in detail shortly. Now the symbol for a transformer is this. So these are the wires that we have. So this will be the primary and this will be the secondary. Now this one here is called the soft iron core. So that's how you represent the soft iron core. The symbol consists of two curled lines representing the coils. These are unconnected. The lines, sometimes 2 or 3, are drawn. In the middle, they represent the magnetic link between the coils. That's this soft iron core. It represents the magnetic link between the coils that is made by the soft iron core. Now let's look at an example. The example says Vp is equal to 20 volts, Np is equal to 600, Vs is 200, and S is what? We do not know. Now the transformer equation, or the turns ratio, is Ns over Np is equal to Vs over Vp. So Ns over Np is equal to Vs over Vp. Now our Ns we do not know. Np is 600. So Ns over 600 is equal to 200 over 20. Then you make Ns the subject of the formula by multiplying by Np both sides. So multiply by 600. So it will be 200 over 20, which is 10. 10 times 600, that gives you 6,000. Second example here. Vp is 6 volts, Np is 50, Vs is unknown, and Ns is 2000. So Vs over Vp is equal to Ns over Np. Now making Ns the subject, we'll just simply multiply by Np both sides. So we want to make Vs the subject. So Vs over Vp, so multiply by Vp both sides. So it's going to be 2000 over 50, which is 400, right? It should be 400, yes. So 400 times 6. So that's 2000 over 50, that's 40. 40 times 6, 240. Yes, so 240 volts is going to be our voltage in the secondary. Last example. A step-down transformer is to be used to operate a 12-volt bulb from a 240-volt main supply. There are 500 turns on the primary coil. If the current in the primary coil is 0.50 amps, calculate the number of turns in the secondary. So NS over NP is equal to VS over VP. Our VS is 12. Our VP is 240. So 12 over 240 times 500 is going to be that. Then B, the current in the secondary coil. Current in the secondary coil, again, we know VS over VP is equal to IP over IS. IP over IS. Please take note of that. So if you do the maths well, let me know in the comments. If you manage to do it, you should get 10 amps. Should get 10 amps. Right, so I'm going to cut the video here and continue with high voltage transmission of electricity in my next video. Signing out.